I believe that even if you are still not able to understand all that story about decimation and interpolation, we can just write down the equations and we can apply them. So I believe that it is going to be the easiest way how to go on. So afterwards, you can take some time and I mean, in afternoon or tomorrow, any day after, you can just find out how does it work. But now we can just use the final equations. Again, I will share the presentation. The lecture topics are decimation and interpolation by factor of m. Today, we are going to skip that part and we are going directly to two-band filterbank decimation and expansion. So I will just jump to slide 14. Okay. I will just for a minute stop sharing because I would like to introduce what are we going to do. Okay, stop. I will change the camera. Here it is. So at the very beginning, we had a two-band filter bank. At the very beginning, that filter bank was without any decimation and interpolation. We had only the wires in between. Okay, I'm not going to put that wires in this moment. It was pretty simple to choose the 4 filters and to have a perfect reconstruction. We had a large freedom of choosing the coefficients of these filters. And then we decided to introduce, we said it is fine, it is okay for some analysis purposes, but for example, for compression, if you have 1,000 samples here, you have 2,000 samples here, which is a little bit out of the purpose. So we have introduced something that was called decimator by the factor of 2. And this is, let's say, where this is the transform domain or image. This is the signal, this is the image. And on the other side, we introduced inserting zeros, and we call it expansion or expanders. Okay, if you have some, this is denoted as X. So when it goes through the filter H0, we have to use another letter for that. So I'm going to use Y0 for something that goes here, and Y1 for something that is actually the output of the high pass filter. And then we apply the decimation. It was like V, and after inserting zeros, we had U. It was right here. Notice that actually we need U to calculate the overall frequency response or the response in the time domain. So this is what we need, and it was not so bad when we were talking about U. It was kind of weird because it had that square root, and it is not so nice. So to distinguish the upper one from the lower one, I'm going to add 0 here, and V1 and U1 will be here. Okay. So what happens to something that goes through decimator? Weird things, but U0 was 1/2 of the y0 plus something like this. So y0 of minus z. And this is our final result. So what happens when you actually so let's say the input y0 could look like this, and what happened here, let it be red, what happened there. So instead of having this, instead of every second sample, we actually insert zeros. So this guy survives, this guy survives, and this guy survives. And this guy and this guy, they were put actually to 0. So this is U0. And this is how it looks like in Z domain. So even if you do not understand why, you can understand that this is the equation that describes U0, and the same stands for U1. So what do we have? Before, when we had no decimation, so when we had a simple filter bank, X, and so the overall transfer function was actually cascade of the two, which means F0 times H0 plus F1 times H1. That was the overall transfer function. So the cascade corresponds to the product, cascade corresponds to the product, and we have a summation of the two terms. So that was, or if I want to say that x hat was this times x. So this is the complete equation in this case. So what happens in this case? Okay, at first, y0 is h0 times x, y1 is h1 times x. So the simple filtering. Then we have to apply this equation here and here, so twice. And finally, we have to apply f0 and f1 to get the overall equation. Now I'm going to the slides. So let's say the first line, the first equation corresponds to non-decimated system where we have a wire in between. So F0 times H0 plus F1 times H1 must be 1, or okay, maybe some delay. That's fine. So that was perfect reconstruction condition for our non-decimated system. Okay, but what we have now? Okay, we have a more job to do. So let's express for the beginning U0. U0 is actually everything from the left-hand side, H0 times X. Okay, nice. But plus H0 of minus Z times X of minus Z, we have to add them together and multiply by 1/2. So that is what happens here. We must apply the red equation on y0. But y0, of course, is h0 times x. So this is what we do. And now we have u0 and u1. To get the reconstructed signal, we have to apply f0 and f1 as well. So f0 to u0, f1 to u1. So let's go on. So our so what we need, I mean, what we need to get this equation again. So it is hidden inside of our story. It is hidden, and right now we can do it like this. So it was so we need to get that f0 times u0 plus f1 times u1 is equal to original signal, eventually delayed. That's what we want. But the bad thing that our overall equation contains terms with minus signs, minus z, that are kind of result of decimation and expansion. And this is something that we do not want. So we will split the result in a part that is already familiar with us, which is the good part, and let's say the bad part. So let us assume that we have that this H0 is a low pass filter and this H1 is a high pass filter. I will stop sharing so we can go back to this, or maybe I can just draw it again. Let us imagine for the moment that H0 is an ideal filter, like we already have that example on the previous lecture. So let the input spectrum be something like this. Okay. We apply ideal low pass filter. So what we have right here is something like this. Only half passes. So we cut it. And this is the ideal high pass filter. So only this part remains. Okay. So right here we have a decimation, which means that this spectrum will be expanded from pi half to pi. So the same picture, but expanded to pi. And here it will be also expanded. Okay, I will just leave. I will not put any marks down. Okay, so what happens here after inserting zeros? After inserting zeros, it will be again compressed and repeated. And right here, okay. And now we understand why we need, again, the ideal low-pass filter and the ideal high-pass filter. I mean, without these guys, it was some kind of redundant. But right now, we understand why we need it. We need it to cut out the proper parts. So This guy will cut the low pass part, and this guy will cut the high pass part. If they are ideal half band filters. And altogether, we are going to get the perfectly reconstructed signal exactly as we wanted. So now we understand that if we apply the ideal filters, I mean, only by graphical, in a very simple way, we can understand that this is again a perfect reconstruction system, in spite of the fact that we are throwing away the half of the samples in both channels. F0 and F1 somehow helps to go back. They are killing the repeating part, the one that is not something that we want. And finally, we get the same result as we had no decimators and expanders. So much about ideal filters. But we said that it was not easy to have ideal filters. They have infinite impulse response. We can only, in practice, we can only approximate the ideal filters. So if these two guys are not ideal, but some real filters, maybe we will not have the perfect reconstruction, but maybe it could be an approximate reconstruction. So the low pass filter in the synthesis part and the high pass filter in the synthesis part, they have their role. They must kill the repeating image of the spectrum, which was actually introduced by inserting zeros in between of the samples. Now we understand why we need them. So we need them to kill the unwanted part of the spectrum and to get back to our signal. So I will go back to the presentation. So let us assume for the moment that we have some real filters. They are not ideal, but let H0 be some real low-pass filter, so its frequency response can be depicted like on this page. And yeah, the high-pass filter can, of course, some real one can look like this. So what we have is that transitional area of filters surpasses pi half, and we expect some mess. We expect some aliasing. So let's check it out, how it looks like in more real example, not so ideal as on the paper. We start from the same example. So let X here denotes, let X denote the spectrum of the input signal, like this one. I mean, it also has the left-hand side and so on. It repeats. And let the dashed curve represent the, let's say, real low-pass filter. So what happens when it goes through? We get something like this. So this part is preserved, nicely cut, but transition area makes it a little bit messy. Okay, it goes over pi half. And then we apply the decimator. What happens? It is expanded. And since it is expanded, I mean, it it has two parts, two terms. In our equation, we have two terms. Now it is depicted by white and gray, and these two terms overlap each other, so we have some mass around pi half. Okay, that's u what we have finally, and then we apply again a low pass filter f0, which is also non-ideal low pass filter, so something will survive. So except for our wanted signal, there will be some aliasing part. That is the part with the minus sign in equation. So this is the bad guy, this is the good guy. And okay, let us see what happens on the high pass side. High pass filters are also not ideal, so this part is nicely cut, but here we have some transition area that goes over the pi half. After the decimation, we have two terms, and these two terms mix together. So we have a white one and a gray one. Okay, let's check it out what happens after inserting zeros. After inserting zeros, it is stretched and multiplied. The gray one is bad one. We don't want to have it here. The white one is okay one. And finally, we apply a high pass filter. It kills most of the gray one, but something survives. That what survives is depicted in the lowest row, the third row. Okay. Okay then. So even with some real filters, we can achieve approximate perfect reconstruction. If we have a not ideal but good filters that are actually selective, that are good half band filters, in that case, that aliasing part is not very big, and maybe one can say that we can live with it. We can live with some a little mistake of such a filter. But engineers are engineers. They are never satisfied. They always try to do something better. So if we put all the equations all together, so we can see that the upper part here, F0, applies to, let's say, the good term and to the bad term. In lower branch, high pass filter applies to the good part, and the bad part, aliasing part, which consists of minus parts. And maybe we can just go in our thinking completely in a different way. Instead of having ideal filters, instead of having their approximations of ideal filters, maybe we can have lousy filters, the worst filters ever. Maybe this low pass filter can be even the simplest possible low pass filter, and H1 be the simplest possible high pass filter. Okay, but what then? Aliasing part is then great, big, and it is not good for perfect reconstruction. Only if we achieve, but it could be if we achieve that the two aliasing components cancel each other. So if we achieve that the gray part, look, this is the high pass filter, and this is the aliasing part. These are the aliasing parts of the high pass filter. Now I'm going back a couple of slides. Here, this is the aliasing part of the low pass filter. Actually, they are in the same place. Page 18 shows the aliasing parts, the bad parts in the upper branch, Page 20 shows the bad terms, aliasing parts of the lower branch. If they cancel each other, they can even be big, and they will disappear from the final result. So that is our idea. So we just split the original perfect reconstruction property in two parts. One part consists only the aliasing components, the one with minus signs, and we want it to be zero. This is our idea. And the other part consists only of the positive parts, and the result must be, okay, not one because of these two halves, it must be two to achieve the perfect reconstruction. Altogether, we have two conditions. One is perfect reconstruction property, which is actually almost the same as it was for the original filter bank. And we have that aliasing cancellation condition, which actually achieves that even if we have aliasing, if we have a heavy aliasing, a heavy overlap of the spectral parts, we still can achieve perfect reconstruction by its cancellation. And that is the point where we have that we will end our lecture for today. So the idea is how to achieve that, and we will talk about it next time. So I will stop sharing this, change the camera. Okay, so once again, we have introduced the decimator and expander, and that in a part of our filter bank. What was the consequence? The consequence was that actually the spectrum of the original signal overlaps due to throwing away half of the samples. One idea was to use the ideal filters. In that case, aliasing parts can be cut out. The other idea was to use approximately ideal filters, so something very selective filters. In that case, the aliasing parts will not be big enough, so we could have almost perfect reconstruction. But the best idea was okay, let's go and use lousy filters, but let us design it in such a way that the aliasing parts from one branch cancels the aliasing parts from the other branch. Even if we have 10 branches in some systems, maybe we can design the filter bank in such a way that the aliasing parts cancel each other. And that was the most brilliant idea that will bring us to decimated filter banks that are useful, and they have exact perfect reconstruction property.